Cool. Hi, everyone. Again, I'm Pulkit. So for the next couple of lectures, we're gonna learn more about medical segmentation, but this time with deep learning. Um, so the way that I've designed the slides is like a single slide deck. So whatever we are not able to cover today, we'll cover in the next class. So for today, we'll start with some state-of-the-art segmentation papers, some key papers. Then what I'll do following that will be like a tour of different concepts within the field. So domain adaptation, generalization, meta learning, attention mechanisms, domain disentanglement. And then in the next lecture, we will cover representation learning, specifically self-supervised learning, multitask learning. And then we will close the second lecture with transformers and some shape bias stuff. So these couple of lectures are going to be more like a tour of how the field has been since 2015 until the current day. So if you don't understand some concepts, I'll hang around after the class to discuss more in detail. But think of it as like giving you like, hey, here are the different things in the field, and you can go and look up more information at the links and at the papers. So let's start with the key papers since 2015 in deep learning for segmentation. And as you go through the slides, keep in mind there are three different things which have evolved over the years. The first is like the architectural choices, the loss functions, and what priors are incorporated within deep learning.
Just 1 second. So two things. First one, did you need to ask about the recording?
Oh yeah. Okay. Also, the class is being recorded by from the back, so I think most of you won't be in the lecture. It's just gonna be me who's gonna be recorded.
Okay. If you don't want to be in the recording, you can have a chance to move first real quick. If you don't want to. The other thing I wanted to tell you is this is what. Okay, thank you. This is what's coming out in Zoom, if that's okay with you. Like it's showing not presenter mode, but it's fine if it's fine with you. But if you have like notes that you don't want to be on Zoom, then
I don't need the notes actually.
Okay, maybe
So
maybe if you turn off presenter view.
Did this change on Zoom?
Yeah, that works.
Yeah. Okay. Thanks. Yeah. So as we go through the slides, just keep in mind the following three things: how the architectural choices have evolved over the years, how loss functions are being differed between these different papers, and how priors, both implicit and explicit, have been incorporated into these deep learning methods. Second thing to keep in mind is what data augmentation strategies, post-processing strategies, and different data sets are being used in these papers. So just to set the stage, you are already aware of three different kinds of segmentation. The first type is instance segmentation, where you are interested in only the foreground, but not the background. But in the foreground, you're interested in every class of that particular object. So if you have the two cows over here, you want to label the different instances as cow number 1 and cow number 2. The second type of segmentation is semantic segmentation, which is the topic of today, where you're interested in both the foreground class and the background class. Well, in the background classes, you want the different classes to be differentiated, and the foreground classes, you don't want the individual instances to be picked apart, but just that, hey, there is a cow, there are trees, a sky, and grass. Now, if you combine instance segmentation with semantic segmentation, you will get something called panoptic segmentation, which has been the most recent interest in the field, where you want the background classes and also the specific instance of each of the foreground classes. So let's dive in. So for semantic segmentation with deep learning, what we want is, you already know, there is an input image here. It's a 3-channel image with a height and a width of a natural image. and the output that you're interested is in the different classes. One thing to note here is that the input channels over here are the 3 RGB channels, and the output is C times H times W, where C corresponds to the number of classes. And then finally, you can do an argmax over the probability distribution to get the final segmentation. Well, in deep learning for medical segmentation, this would change to D, where D is depth, height, and width. And your output would be C times D times H times W. So number of classes times the depth, height, and the width. So for deep learning segmentation, it's as easy as stacking up a bunch of convolution layers, one after the other, to map the input to the corresponding output. But there is one problem with just stacking convolution layers one after the other. First is that with this particular network, what will happen is that you will increase the computational load by a very high factor. This is due to you will be just like over here, you have a bunch of convolution layers. And what you're doing over here is just by stacking them is just operating on a high resolution input. So what you want to do is to degrade your resolution while you design your network. The second thing is that if you just take the entire image and you try to get the output segmentation over here, what you're essentially doing is for every pixel in your output, you need to have many layers so that you are able to see the entire receptive field in your input image. So that is the second drawback of having just plain convolution layers one after the other. So to mitigate these two drawbacks, what we essentially do is have an autoencoder, which you might have seen in the previous few classes. So the advantage of using this autoencoder is first you have this downsampling leg, and then you have this upsampling leg. The main advantage over here is that you are trying to take the high resolution input and map that to a low resolution input, and then again take that low resolution input to map it back to high resolution. So that way you are trying to reduce the number of computations required when compared to just using plain convolution layers. So essentially, this is what we are going to do. Every architecture from here onwards is going to be this autoencoder, where you have an input and your output is what you are interested in. Any questions so far? How do I see the questions?
So you have to flip over to the PC.
Oh.
On the panel. Good. Yeah,
oh, like the VGA?
Yeah.
Oh.
I'll just read.
I guess, yeah.
Oh
yeah, okay.
Guys, just ask a question. Wait.
Yeah. Yeah. So one thing to note before we begin is that in medical imaging, since you are limited by the computation that you can do on the GPUs, we train all the networks as 3D patches. So you're not inputting your entire image one at a time, but you give random patches from the image into the network. So I'll come back to this. Also, as I go through the slides, look out for these red boxes where the key message for that particular slide is in the red box. So one of the first papers that came out for segmentation is nnU-Net back in 2015, which is probably the most cited paper in the community. Again, this is just a simple autoencoder architecture where you have an input image of size, let's say X, Y, and a channel with one channel, and the desired output is a segmentation map, again, of similar size, and you have output classes as two, the foreground and the background. So these are just essentially convolution network layers stacked on top of each other, but in an autoencoder fashion. And these are something called skip connections, which probably is the most important addition to the network. So what happens here is you have an input image. Then the first thing that you have is you have a bunch of convolution layers. You have max pooling to downsample the image. And this leg of the network is called the downsampling network, which basically captures the context within the given input image. The next thing that you have is something called latent features, which essentially captures whatever there is in the image into some low dimensional space. Then in the third leg, we upsample the image using a bunch of convolution layers and transpose convolution layers and max unpooling functions, so that your resolution of the image or the size of the image is now back to the original size, similar to the input image. Now, this particular leg is called the upsampling leg, and this helps in localization of the structure of interest in your input image. The key important part over here is the skip connections, which is basically you take your input from the corresponding layer and you concatenate that with the output coming from the second layer. So what it does is that it takes the low-level features from your downsampling network and it concatenates that with your upsampling network. So this helps in giving the network a sense of where to look for the features and localize your input target in the images. So that's why it's called a unit, because of this U shape. It's nothing but an autoencoder with skip connections. Finally, you can have a loss function of your choice, which you might have seen in the previous lectures, such as dice loss or cross entropy loss, any surface-based loss. So these are some example segmentations on a cell tracking challenge, where this image on the left are cells. The segmentation is shown in the cyan color, and the contour in yellow shows the ground truth. And again, on the right is another data set where you see some different cells, segmentation in different colors, and the yellow boundary shows the ground truth. So this challenge, this particular paper won several challenges in 2015, and then it became the basis for all the segmentation networks from there on. Some more examples of where UNet has been applied in the literature. So these are microscopic cell images. These are some neurites, and all the segmentations that you see on the right are in 3D. Some more examples of stained cells and microglial activity. So I hope it gives you a sense of how the basic architecture was proposed in 2015. And from then on, and in the next few slides, try to connect how the different additions to the basic architecture of UNet makes improvement over the UNIC architecture. So we saw that in the previous slide that these skip connections were the main features to get the improvement of the performance improvement. So what next? So the natural question to ask is that if we stack these convolution layers, even in that autoencoder, would that boost the accuracy of your segmentations? And after like empirical analysis and theoretical analysis, people realize that just merely stacking layers won't give you a boost in accuracy. In fact, it would saturate the accuracy after a point time. And that is called the degradation problem, that even stacking more layers would would naturally degrade the accuracy after that. I guess I'll come back to that question. Yeah. Yeah. So in 2015 itself, they designed a new architecture, which was first proposed for image classification for natural objects called the ResNet architecture, which I'm pretty sure most of you might heard about it. So essentially, think of any architecture as a stack of convolution layers. And we talked about that it doesn't give you a performance boost after a certain point of time. So the natural way to think about this is, can we incorporate another function within the architecture which might help increase the boost in performance? So that's where the ResNet module come into the picture. So essentially let's just focus on this particular part, which is called the ResNet part. Let me expand this. So what happens is, if you look on the left, you have your output coming from the previous layer, the previous convolution layer. You let it pass through another convolution layer, or whenever I say convolution layer, it comes with any activation function, normalization functions as well. And after that, so you get f of x, take x, pass it through conv layer, get f of x, and then you take the input itself and just add these two things together, right? So it becomes f of x plus x. So what it does is basically not only processes the input a few times using convolution block, but it also adds information from the previous layers to give more context to what is happening at that particular layer, right? This is again expanded on the right. Just to reiterate, you take an input, pass it through convolution blocks, and you take the same input and just add it to the one that you get at the end. Any questions so far? You can just raise your hand, I guess.
There's 3 questions in
Yeah.
the
So these are from class. This is you. Making my time harder. Yeah, so what is copied feature map in UNet? So it is basically the output from that particular convolution block at this particular stage. So let's see over here, you have the output over here, and you have the output from this particular block. So you take this last layer, whatever the output you get at this particular stage, and you get the output from this particular stage and just concatenate them along one dimension, right? Of course, you need some cropping. There is like cropping to be done so that both of them match the dimensions. Which part of the skip connections are cropped? Yeah, does this. Yeah, this does change the size of the image in this particular network, but the newer networks, it automatically takes care of the size, and both the input and output essentially are of the same sizes. So here you can see we go from 572 to 398. So you take a larger image, but you get only the segmentation in, let's say, a smaller part of it. But the newer networks, you don't have to worry about those things. Dash lines. Yeah, I think dash lines, I think we covered this, right? Yeah. So is the dash lines things clear? Dash line is, again, basically the input X that you have from the previous layer. Right. So we look at two things. UNet has skip connections, and then there was an improvement over it in the next iteration where we added ResNet modules, right? Now let's take a segue, and we have been talking about the two architectural details, but now let's talk about loss functions. So this particular slide takes care of whatever you have to know about how the loss functions have been used in the literature. So you can think of loss functions in like two different ways. One is called the fitting loss, and the other side is called the regularization losses. So in the fitting loss, you are already aware of dice loss and cross entropy loss. So anything that is related to the volume of the image, right? That can be divided into this category. And anything that helps in regularization can be categorized in this section, where not only you take like the volumes that you have in terms of dice and cross entropy, but now you have implicit and explicit priors based on the size, topology, shape, and geometry of the output segmentation of the structure of interest that you are interested in the output. So let's say that I'm interested in segmenting the vessels in this particular, I'm interested in segmenting the vessels in this retinal image. So can I have some explicit notion in the loss function, which helps me, tells the network that, hey, this is a vessel and you want to segment these particular vessels. So all that regularization can fit into this particular category. Of course, we'll come back to all these losses in the next lecture as well. Another way to look at this is you have all your different cross entropy based losses on the left. You have everything related to different variants of dice losses over here. Everything that can be combined from these two types of losses go over here. And then anything that takes into account the surfaces between the foreground and the ground truth can be categorized into boundary-based losses. We'll look at the equations in a minute. So I guess cross entropy, you already know from previous lectures, and same with dice loss, which is nothing but intersection over union. So again, the loss is computed between your predictions and your actual ground truth. So cross entropy and dice are volumetric losses. And then you have something called a Hausdorff loss, which basically tries to compute the distance between the surfaces of your predictions and your ground truth segmentations, right? So in 3D, let's say you have a segmentation of your brain, and which is your ground truth, and you have a predicted segmentation of the brain. So you can compute a Hausdorff distance or any surface-based distance between the surfaces of those two structures, right? And then you can always have combinations of different losses, right? I guess these are things that you have already seen. Right. There is another thing that people do when designing these loss functions is to give weights to different structures. So suppose I am segmenting different regions in my brain, and I know that, hey, region 1 has more volume than region 2. So there is an automatic class imbalance, right? So what you can do is you can weight the different regions or the different predictions by the inverse of the volume. So you can give more weighting to a structure which you know which will be missegmented in your output, and give less weighting to a structure which you know that is kind of easy to segment. Okay. So you can always weight your outputs in your loss functions. Couple of other things is to look out for implicit and explicit priors. Priors is, again, a way of giving information to your network to tell them more about what specific structure you're interested in segmenting. This is especially helpful when you know a priori what kind of output do you want from your network. Yeah, so the next paper that I want to discuss is nnU-Net, which is nothing but U-Net that you saw with ResNet modules and a bunch of other nitty-gritties. And this is arguably, in our opinion, in the lab, probably the state-of-the-art segmentation network for medical images. You can, I highly recommend like go and have a look at this paper, look at the GitHub repo, and if you want to try, please do so. It's really easy to set up. And they have benchmarked nnU-Net on a variety of different anatomies across a range of modalities to segment different structures. Here are some of the examples of brain segmentation, cell segmentation, different abdominal anatomies, chest, liver. So basically it takes care of the entire human anatomy from the cellular level to the coarser level of organs. Okay. So as I said, it's a package. So the package takes care of everything, right from pre-processing the data, setting up the different loss functions, the different architectural choices, and then finally it gives a nice prediction. Right? Again, there are many slides, so I'll like skip over some of the slides. But the main thing that we, or the main conclusion that I want you to take away from nnU-Net is that what we discovered is the key ingredient for medical segmentation is how you augment your input data or data augmentation. So apart from just putting in your images, you can also randomly rotate, scale, add noises, warp the images to not only increase your data set, but also make the network more robust to different kinds of images. So we'll come back to data augmentation in the next lecture. Some more examples before we move on to the next architecture. So this is data from our lab where we try to segment the left ventricle of the heart in echocardiography ultrasound data using nnU-Net. On the left is the image. On the right, over here are the different structures of interest. So these are manual segmentations that you're seeing right now. So this is the left ventricle. This is the left ventricle cavity. This is the tract. This is the anterior leaflet, and this is the posterior leaflet. So the network was trained on such ground truth images, and these are some of the output segmentations from nnU-Net. And these are in 3D. Okay. Yeah. So last example of why nnU-Net is really good. So this is again data at Penn where we have ex vivo images acquired from these brains. So these are brains of people who passed away due to neurodegenerative diseases. So this particular brain had Alzheimer's disease. This particular patient had Alzheimer's disease, and this is their brain. So we take out their brain and then we slab them, and then we acquire high resolution images scanned at 7 Tesla and 9.4 Tesla. So let me show some of the images over here. I think it's not as, I can't see much contrast over there, but so these are the three views in sagittal, axial, and coronal of different patients. So the patient that you see on the top row had a bunch of different diseases: Alzheimer's, cerebrovascular disease, Lewy body disease, and over here, the second row, the patient had FTLD disease, which is frontotemporal lobar degeneration. So we acquire these images at 7 Tesla ex vivo, basically after the patient has died. These are some 3D renderings of those MRIs. And then we collect some manual segmentations for different structure of interest. So to start with, we try to segment the cortex, the white matter hyperintensities, and 4 subcortical structures: thalamus, putamen, caudate, and globus pallidus. So on like 4 to 5 different subjects, we manually segment these structures in small patches, and then we pass these through nnU-Net to get automated segmentations. So here are the automated segmentations for the 7 different structures. So the key takeaway again from nnU-Net is that with just limited manual segmentations, like 3-4 subjects of manual ground truth labels, you can generalize it to a whole lot of cohort that you have. So this is just a 3D rendering. So another thing that we observed is that when we trained the nnU-Net on data coming from one distribution that is acquired from one imaging sequence, and then just apply that network to data coming from another imaging sequence, we saw pretty good generalization capabilities. So this is, again, an ex vivo image brain, but this particular brain was acquired at a much higher resolution and also using a different MRI sequence. So yeah, you get some nice, pretty looking images. Right. And as I said, you can also segment right at the cellular level. So these are cells in the hippocampus. So these are the dentate gyrus cells. These are the CA1 subfield of the hippocampus cells segmented in 3D using an nnU-Net on a phase contrast CT imaging sequence. Lastly, before going on to the architecture again, this is another famous toolbox like nnU-Net, which you can use to segment medical images. Okay, I'll come back to this first question in the next class. Implicit and explicit prior will be cleared in a few minutes. And do we manually weight the loss function? Any rule of thumb? So it's more empirically. If you have a combination of, let's say, dice loss, surface loss, and a cross entropy loss, so what you end up doing is having different weights, 0.3 to each, or you can conduct bunch of different experiments and see what is working for you. Okay, so we looked at some ex vivo images right now, where the brain was taken out of the human body and then imaged for a long time. Now let's shift gears and see how can we segment in vivo images, where in vivo means when the image was acquired, when the patient was still alive in a scanner, right? So this is how a typical T1 weighted image of a human brain looks like, right? From the 3 viewing planes. And the task over here is to segment the different regions, or the parcellate the different regions in the brain over here. So over here, you can see you want to segment the cortical ribbon, the subcortical structures, the white matter, and any white matter hyperintensity that is present. So these are around, I think, around 95 labels for both the left and the right hemisphere. Yeah, so not sure if you have seen free surfer in the class before, or I guess you have. So free surfer is one of the most widely used toolbox for anything related to in vivo MRI, especially structural MRI. And then now they have a new toolbox where they automate the segmentation process using deep learning. So, okay, so far, all the segmentation networks, especially for medical images that we were seeing, they train the input, they train the networks by using patches from the images, right? Because it's such a large 3D image, you can't fit your entire 3D image in one go in a GPU. So you take patches and then you kind of train your networks, right? Now, here in this paper, what they do is they train this network in a slice by slice fashion. So let's say you have this coronal view of your brain. So what you would do is you take the entire image. So you can see the entire brain at one go. But instead of taking patches, you just take the, let's say, n number of slices. So you take 7 slices and you try to segment the middle slice. So slice number 4 is what you're going to segment. So you have 7 slices over here as your input, and your output would be the segmented slice, which is the segmentation for the middle slice, right? So what you're doing is you're avoiding giving patches, small regions. So you're actually giving the whole context of the image. But since, again, you can't fit into a GPU, you're just giving 7 channels and try to predict output for 1 channel. And then you can repeat it for all the different slices, right? Right, so what I showed you here is for the coronal slice, right? So again, this looks like a unit, right? You have this U-shaped structure, you have these skip connections, right? But one thing that they do differently, or 2 things that they do differently. The first thing is that in U-Net, if you remember, you have output from this particular layer, and you have output from this particular layer. In U-Net, what they do is they just concatenate the 2 features, right? Over here, what difference they make is that they take the 2 features, one coming from here and one coming from here, and just do a max operation. So whichever feature for that particular voxel has a higher value, they take that into account, right? So this is what I'm trying to explain. So in U-Net, you have, let's say, a 3x3 cube coming from here, and a 3x3 cube coming from here. You concatenate that, and then you get a 6 channel over here. But in this particular paper, you have the 3x3 from 3x3x3. You have from the both legs, and you just take the max at every particular voxel, right? So this is the third architectural change that we have seen so far, right? Right. So, and the rest of the structure, you can stack them. These CDB blocks are nothing but dense blocks for convolutions and different nonlinear activations. The second change that they have in this particular paper is that that is what I was talking about. So they have a 7-channel input, and they have 1 channel output for that middle slice. And you can repeat this for all the slices for a given subject, and you can get segmentations for all the slices, right? But the thing to note in medical images is that you have 3 viewing planes: coronal, sagittal, and axial. So you can run this network on all different planes, one after the other, right? So you can get segmentation for all the coronal slices, then all the axial slices, and then all the sagittal slices, right? So take this network, train it 3 times, one for axial, coronal, and sagittal. That way, for every voxel in your output, you will have 3 segmentation values, right? One when you segmented it for axial, one when you segmented for coronal, and one for sagittal, right? So for every voxel, you have 3 values, and what you can do is you can do a voting average between those 3 values and choose that particular label for that particular voxel, right? So this strategy is called view aggregation, and it is a post-processing step to get a segmentation value for one particular voxel. Right. So again, just have a mind map of how things have evolved. So this goes into post-processing step. And we have seen 3 different architectures so far: skip connections, ResNet modules, and this max out operation. So next thing is, again, the task remains same in this particular paper called DeepNet, which was actually a precursor of FastSurfer. So here again, the task is same. You have your input T1 weighted MRI, and you want to get labels for all the different regions in the brain, right? So they do it in 2 steps. Don't worry about this foreground background. So first, what they do is they get this foreground background extraction, and then they segment this into more regions. So in this particular paper, there are 2 things that I want to highlight. One is this post-processing using CRFs, conditional random fields, which you might have seen in the MRF lecture. And the other is the notion of priors. And in particular, we will look at eigenfunctions. So what I mean by prior, both implicit and explicit, is prior is any information that you're externally giving to the network so that it knows more about your particular modality of interest and your particular anatomy of interest, right? So I'll give you a concrete example using eigenfunctions. So implicit is something which you can think of it as like putting into the network architecture itself. And explicit, I would like to classify that as something which comes from a loss function. So priors can go both into architectures and also they can go into loss functions, right? So again, the task here is using deep learning segment the brain into different regions. So we'll have a segue here for one slide. I want to explain what Laplace-Beltrami operator is. So you already are very familiar with taking gradients and divergence in your images. You already know what a Laplacian is. Laplacian is in a Euclidean plane, nothing but taking the divergence of your gradient. So if you look at this particular equation, suppose f is your image, right? And you take a second order partial derivative in the x direction, and you take second order partial derivative in the y direction, and you add those things together is what is called Laplacian, right? So you have already used that in your Laplacian filters. Now, this is what we do in Euclidean space in your normal 3D coordinate geometry. But if you take this to surfaces and if you take this to non-Euclidean geometry, or like, so that is basically called Laplacian, like apply Laplacian operator in manifolds. That is, take Laplacian to non-Euclidean geometry, and that is called the Laplace-Beltrami operator, right? So why I bring this is that suppose you have your 3D segmentation of a brain. You are very familiar with voxels. Now you can discretize it somewhat more and convert that into a mesh representation. And then you can apply this Laplace-Beltrami operator on that 3D mesh to get your Laplacian on a non-Euclidean surface, right? So yeah, this is what you have to know. Apply Laplacian to surfaces and meshes is called Laplace-Beltrami operator. So one thing to notice over here is that when we are trying to segment 3D images in the brain, the left hemisphere and the right hemisphere, even if we give them different labels, they are still pretty much the same thing, right? Because you can just take reflection along one of the axes of the brain, and like this particular part is kind of identical to this particular part of the brain. So the left hemisphere and the right hemispheres are similar, right? And even if you give them different labels, the network still might get confused as to what that particular region is. Do I have to mark it as left, or do I have to mark it as right? And So how do we incorporate that information in the network, right? So how do we incorporate that as a prior within the network architecture? So something that we know about this particular brain structure, and we are giving some more information to the network so that it is able to learn what exactly is a left hemisphere and a right hemisphere. Right? So this is something that we are trying to incorporate in the network architecture. So that's where this particular Laplace-Beltrami operator comes into the picture. So what you can do is from your output, that is your ground truth segmentations of your brain, you can compute a spherical, or sorry, a mesh out of it, and then apply the Laplace-Beltrami operator to that mesh. And then you can compute the eigen decomposition of this Laplacian. So delta F is the Laplacian. And if you can compute its eigenvalues and eigenvectors, those eigenvectors in non-Euclidean geometry are called, let's say, eigenfunctions. So this is how an eigenfunction looks like. So take your segmentation, convert into a mesh, and get these eigenfunctions for that particular subject, right? So now I can take this particular information, and along with my input image, I can just give this eigenfunction as well as input in a different channel, right? So I can concatenate my input image, I can with this particular eigenfunction, and pass that through the network to get my segmentations. So the benefit of these eigenfunctions is that it kind of gives implicit representation into the network of what is the left hemisphere and what is the right hemisphere. So it defines a coordinate system, right? And once you have a coordinate system represented in the network, you know that, hey, this is the left part and this is the right part. Right? So that's the key takeaway, how to give information into the network. How does MRI work for ex vivo scanning? I think this is more like an MRI physics question, which I have no idea about. Does UNet always require pairwise ground truth for training in the task? Yeah, it requires pairwise ground truth. How are the 7 slices being used to improve the one segmentation output in FastSurfer? So yeah, as I said, the 7 slices, so you're not giving them as patches. So it sees the whole context of the image together. And for a segmentation, so for a segmentation of a particular voxel, so you have a voxel and you want to give a class to it. So what you essentially do is you look at nearby voxels, right? So this is essentially what those 7 slices are doing. It is it's like patch-based segmentation. It is taking context from the first 3 slices, the slide under consideration, and the slices at the back. So it gives more context to segment that particular slice. So yeah, coming back to this, so I talked about eigenfunctions of how to incorporate priors into the network. Another thing which people generally do is once you get the output probability map in your, once you have gone through your entire network, computed your loss functions, and you get a probability map, is to kind of smooth out the probability distribution. And that you can do using a conditional random field, right? See that we don't have much time. So if there is like some slides which don't need much attention, so I'll just skip or like go a bit fast through them. One last thing, or second last thing in this architectural development is something called attentions. So again, you have this UNet architecture with skip connections. Remember, we have been talking about how to concatenate features from the previous layers and the current layer. So we looked at 2 things. One is to concatenate, and then in the FastSurfer paper, we looked at max out operations. Here, what we do is introduce another what do you call function called attention mechanism. So I'll explain in a bit what attention is, but what it does is basically it again takes features from the previous layer and the feature from the current layer. And for every particular voxel or every particular feature map in this between these two outputs, it kind of compute a dot product between them. So, and we already know that dot products are used to compare similarity between two different vectors. So if you can compute a dot product, or if you can add these two things up, it can tell you where to look at in that particular image for a given segmentation region. I'll show a picture, it will make it more clear. So basic idea of attention is to focus on a particular region in your image so that the network knows where to look at to segment that particular region. So let's say we are looking at this and this network output. So what we are essentially doing is taking the two features from the previous, from the layers under consideration, and then just compute a simple, you can compute a addition between these two features, and then pass it through some layers, resample them, and then whatever feature you get after that addition, just multiply that or have a dot product of that with one of the layers that is coming from down. So take this feature map, take this feature map and take this feature map, add them together. So this is voxel-wise addition. And then whatever feature that you get from that, again, multiply that with that additive component to get a feature which you can then concatenate over here. So it's just small architectural variants, but the basic architecture still remains a unit, right? Or autoencoder. So what I want to show you over here is taking from left to right. Our task is to segment the pancreas in these images and the kidneys and the spleen. So we are interested in three structures: pancreas, kidney, and spleen. And from left to right, these are the output which you can see overlaid on the MRI image as the training progresses. So from left to right, epoch number 3, 6, 10, 60, and 150. So you can see that I'm visualizing just the attention maps or the things. I'm visualizing this particular alpha, which you basically get after the addition. This is what I'm trying to visualize. And what it does is basically tells the network as to where to look in that particular image to segment the structure of interest. So as you can see that as the training progresses, the network is much able, it's better able to learn where to look at to segment the structures. So first it looks at the entire image, and then it fine grains itself, and then keeps on looking at the structure of interest. So that is the benefit of using these additive components as attention mechanisms in the paper. Let's get this. Cool. One last thing I want to mention is this idea of having attention mechanism of to have fine-grained segmentation knowledge in your networks is something called squeeze and excitation networks. So think of it as like how we discuss about a ResNet module. So you can integrate such a module inside your network, just as you integrated a ResNet module in a skip connection manner. So what it does over here is that, let's say you have you're somewhere in your convolution block, and the output of that convolution block has a size of H, W, and C. So your height, width, and number of channels, right? So what we try to do over here is to try to recalibrate the features by expanding them in one dimension and contracting them in other dimensions. So just follow the cursor. So what I'm doing over here is I have height, width, and number of channels. So what I'm doing here is squishing all the knowledge along the HW plane into one channel, right? So I have channel number 1, which is of size H times W. I take all the voxels from that particular channel, sum that up, and I get one value, right? And I can do that for all the channels. So essentially what I did is that from size HWC, I just went to this vector of C, right? Does this make sense? So I'm squishing all the knowledge and just converting everything into just one single channel, right? And then I can just place these things, these channels again to get the size again, which is HW and C, right? So first I squished all the channels. I've squished all the voxels in one plane into these channels, and then again I excited them and made them back into this into the same input size, right? So it's just recalibration of features. And I can do this again in the other dimension as well. So I can retain my height and width, but take all the information from the channels and make them into a one value, right? And again, I can excite those channels again to have height, width, and channels as my same input output dimensions, right? So it's just squishing and exciting in different dimensions to recalibrate the knowledge learned implicitly. And again, nothing stops us to combine everything together, right? So yeah, so these blocks are called channel and spatial excitation blocks, squeeze and excitation blocks, which you can just place in your network just as you do in your ResNet architectures, right? So finally, before we move on, this network called nnU-Net, I just want to show you here how whatever we learned so far in terms of architectural details, it ties up together in this particular network. You have your unit architecture over here with skip connections and convolution blocks. And within each convolution block, you have your residual block, and you also have your squeeze and excitation block, right? So just stack everything together in this network, and then you can benefit from all these different architectural changes. So I hope now you got an idea of how architectures have evolved over the years and how you can improve accuracy and your segmentation performance by just recalibrating features throughout making small architectural differences, right? Just to mention, whatever we saw so far was in Euclidean space, but nothing stops us from using these networks to non-Euclidean spherical surfaces or conical surfaces in mesh-based architectures, right? And just to mention a paper from the lab, deep label fusion, I encourage you to look at this paper. So what you did in your assignment 2 and 1, I think, where you have multi-atlas segmentation using non-deep learning methods, you can extend the same idea of multi-atlas segmentation to using deep learning. Right. It's a good question. How is attention different from skip connection? So skip connections are giving you overall like a rough context by just concatenating whatever is there, just plainly concatenating. It's giving you context from previous layers, but it's just do it in a vanilla fashion. With attention mechanism, since you have this operation of explicitly adding the features and then having the notion of a dot product, which compares the two input features. So that gives you a very localized sense of having context. That's the simplest explanation. Question is open. Yeah, so this is part of research, how to determine what will work. So you try out different things, then go and reason about them until you have a what? Yeah, I guess nothing stops you from using attention, but having this multiplication or actually a dot product is much more sensible, as dot product, as we are interested in measuring similarity, and dot product is the one which gives you similarity. Okay. Hey, any questions apart from this? You can just ask directly as well. We have 30 minutes and we have a lot to cover. So I'll just get started. So again, so we have seen a lot of architectures. We have seen whatever there is to see the main papers in the field in terms of architectures. In the next lecture, we will look at a variety of loss functions. And that would be, again, using transformers, representation learning, and shape and topology priors. So in the next half an hour, what I'm going to do is introduce you to 2-3 different paradigms in the literature, give 15 minutes each, and see how these different paradigms have been tackled by segmentation. So domain adaptation and generalization using meta-learning. So just to set the stage on what the problem is. So if you focus on the figure on the left, right? So let's see, your task over here is to classify different objects, horse, house, guitar, dogs, right? So the task is a classification task, right? But the thing that you notice over here is that at training time, right, you get a bunch of data which you don't see at test time, right? So at training time, what you see is you see a distribution X, like the data is coming from distribution X. And at test time, you have no information about what that data looks like, right? So over here, let's say you at training time, again, your task is classification, but at training time, you have images which look like photos, images which look like art paintings, and images which look like cartoons. And in all these different data distributions, right, you want to classify what object that is, right? So at training time, you have these 3 distributions: photos, art paintings, and cartoons, right? But at test time, you're given the task of, again, classification, but the images are coming from a totally different distribution. So this time the images are coming from sketches, right? So this is something called domain shift or a covariate shift, where the distribution, the statistics of the distribution at test time is different from the statistics of distribution at training time, right? And deep learning models, they will fail if you train them on one distribution and you try to test them on another distribution, right? So one more example is that you have these digital classification tasks where images are coming from the synthetic MNIST data set. You have street view housing numbers, you have your signs, and you have your MNIST-M. So you have these different data distributions, and you are given some data distributions during training, but you want to test it on some other data distribution during test, right? So there is this covariate shift in the statistics, and you want to mitigate that, right? So in terms of medical images, again, data comes from many different distributions. So over here, you can see, let's say I'm interested in segmenting this brain, but the data comes from 3 different scanners: GE, Philips, and Siemens. Now, if I train a network which is trained on only GE and Philips to segment the brain, it might very well be the case that the network might fail to recognize or to give good segmentations when just tested on Siemens scanner, right? And again, some colonoscopy data where you have different light distributions of blue and white. And again, brain images coming from different data sets also have different distributions. So what is the difference between domain adaptation and generalization? So it's better to give an example over here. Domain adaptation is when at the time of training, you have some knowledge about the test data. In particular, you have a lot of training data or like a lot of ground truth labels for these three distributions, but you have very limited training data, or you have a lot of unlabeled data for your test distribution, right? So that's domain adaptation, that there is some knowledge given about your unseen domain. Generalization is pretty much similar, but at the time of training, you have absolutely zero knowledge about what is going to be there in the test data set. Right? So one of the main things that you want to do is, if you look over here, that what we are trying to do is to mitigate the distance or mitigate the statistics between the training and the testing distributions, right? That is the goal of domain adaptation. So you want the network to be invariant to the shift in the domains. So the network should not be able to classify where the data is coming from, domain 1 or domain 2. But it should be discriminative enough that it knows the actual task is actually to classify that image or to segment that particular image, right? So your task over here, let's discuss this particular paper. And your task over here is to, again, as I said, label objects or classify these objects. The training distribution, let's name it the source data set. The testing distribution, let's name it the target data set. Your task over here is classification. And the other task that you have is to make sure that the distributions are well matched between training and testing domains, or the source and the target domains. So this is what a vanilla architecture looks like, where you have your input X, which can come from either your source data set or your target data set. It goes through this feature extractor part. And the first loss that you have is your class prediction loss, where you're predicting what kind of image that is, a horse or a cat, right? And the second leg of the network is basically take these features and have another loss function, which classifies what distribution that particular image is coming from. Is it coming from your source data sets or your target data sets, right? So again, your source data sets, the three data sets that I showed on the left, you have a lot of training examples for that. In fact, a lot of label training examples. But for your target data set, where we want to adapt to that particular domain, you only have very few labeled examples, right? So that is why we need domain adaptation, so that only using those examples, we are able to generalize to a much larger distribution or larger population. So the key ingredient over here is this gradient reversal step. So once you have this classification loss and a domain loss, you have this gradient reversal step, which basically multiplies your gradient in this direction by just a -1 or a negative any floating point that you want. So the intuition behind this particular network is that you're trying to bring the features from the source domain and the target domain together, right? You're trying to confuse the network essentially over here, whether the input image is from the source domain or from the target domain. Because if you multiply the gradient in the backward direction by -1, it will get confused whether this is domain 1 or domain 2, that is source domain or target domain. because at this point, you're no longer trying to classify it correctly. You want to confuse the network that this is domain 1 as well, this is domain 2 as well. So yeah, so the key point is to bring the features together by doing this graded reversal step between the source distribution and the target distribution. I think I'll have to skip that. I'll skip. I really wanted to cover this, but I'll skip this for now. I just want to mention some applications in medical imaging, in particular, this paradigm called meta-learning for domain generalization. I'll skip what meta-learning is, but I'll tell you what, again, domain generalization is, where you have a lot of source data set and a target data set, both from a very different distribution, but in generalization, you have zero knowledge about what is going to be there in your target domain, right? So the best way to explain this is to look at these particular 3 data sets. So let's say at training time, I have a lot of, so the task over here is to segment vertebrae in these computed tomography images. That's our task. And the problem that we have is that at training time, let's say I have a lot of label examples for this particular data distribution, where these vertebrae images come from a healthy population, right? But at test time, all my data set is coming from a distribution which have only disease population. So as you can see on the right, these vertebrae not only come from a different CT scanner or a different center, but there's a lot of fractured vertebrae like this one, and a lot of intervertebral discs which are dislocated. So can I train a network which is only trained on healthy population and then try to use the network to get segmentations on a data set which is trained on get segmentations on a data set which is unhealthy? So that is generalization, no knowledge about this at test time, right? And again, there is another data set where you have possibly everything that you can imagine in the vertebrae segmentation data set, coming from distant distribution of low and high dose CT of implants in the vertebrae, major dislocation and fractures, right? So I'll give you just qualitative examples of what kind of different experiments can be done with domain generalization. You can like skip looking at the table and the figures. I'll just tell you how the experiments are designed in these settings. So what you can do is, one of the experiments that we did was, again, the task is vertebrae segmentation, but we want to generalize across different intensity profile, vertebral disc space, and vertebral anatomy. So if you look at a vertebrae from your cervix or from your neck all the way to your back, it has a different structure all throughout. So a segmentation network which is just trained on the upper part of the body, can it generalize to the vertebrae to the lower part of the body, right? So we can do it in repeated fashions where I take vertebrae from upper part of the body, train a network on that, and then without having any knowledge, try to take that network and segment on the lower part of the body. So we divided it into different profiles, and you can try to generalize. The second experiment, as I mentioned before, is train a network on healthy population and then test it on a data set with dislocated vertebrae. Right? And third is that you train on the first data set, which is healthy, and then test it out on that massive third data set, in which the data set comes from different anatomies, acquisition protocols, different orientations, field of views, and a lot of different pathology. So this is how generalization experiments are done, but unfortunately, I didn't tell you what algorithms go behind them. I'll see if we have time for that. But that is done using a paradigm in machine learning called meta-learning. Yeah, I wanted to cover the main topic called domain disentanglement. So again, switching gears, what I'm gonna explain in the next 10 minutes, it's about domain disentanglement. So try to kind of think about what you learned in the previous GAN lecture. A lot of things that we are gonna do over here ties to generative modeling and image synthesis. Right. So let's say our task over here is to do image-to-image translation, which I'm pretty sure you might have seen this a bunch of times, if not in class, but definitely in the media. So let's say I want to translate from photo to Van Gogh or winter to summer, photograph to portrait. What do? I train GANs, but GANs are unstable. So then I introduce something called disentangled representations and try to improve this image-to-image translation and synthesis. Take the question. So yeah, we don't pre-train, or you can pre-train as well. But as far as I remember, this paper does not pre-train, and it is trained parallelly with the other classifier laws as well. Yeah. Cool. So the way that images are made are, you can think of them in like like you can decompose them into two different things: the content of the image or the appearance of the image, right? So over here, let's say you have this mountain range and the lake. The content over here is the shape, the geometry, and the structures in the image, right? So that's your content. And the style is what distinguishes these different mountain ranges and lakes, right? So the style is this one is more wintry, then it becomes kind of fall, and then it becomes summer, right? Or actually autumn, no, spring, and then summer. So this is more like style, able to distinguish the colors in that particular picture. So let's try to break this this massive figure over here, a complicated figure. So let's say I want to translate or do an image translation from this cat to this dog, right? This cat and also the dog, both of them are made up of content and of style, right? So the content in this particular image or for the cat would be the way that it is looking, right? So it is looking more towards left, right? So remember, it's looking towards left, right? And it has these ears and stuff, but overall the shape is more looking left. And the content in this particular dog is more looking towards center right, right? So, and the appearance of this particular cat is what makes it look like cat. And again, the appearance for a dog is what makes it look like a dog, right? So what we are trying to do here is take this cat image, X, take this dog image, Y, and do a image translation between them, right? Make the cat look like a dog and then dog look like a cat. So the first step, what we do is we have some encoders, a bunch of convolution layers with some special details that go into them. and decompose this image into an appearance block and a content block, right? And then we do the same thing for this dog image. Why you have this encoded representation for content, EC, and encoded representation for appearance, right? Now, what you can do is you can have this generator, which you saw in your GAN class. Let's take the appearance from this cat and take the content from this dog, and let's see what we get, right? So we get this new translated image, which has the appearance of a cat. So it looks like a cat, but it has the content of this dog. So remember, this cat was left looking and the dog was right looking, but the generated new cat is more again towards now right looking, right? It is looking more like in the direction of where the dog is looking. So this is what we can achieve, right? And we can do the similar thing, take the content of the cat. So the output would be more left looking, and take the appearance of this dog and make it, and then generate this particular new dog, right? And then nothing stops us to take this image again and then decompose this again into appearance and content, and then content and appearance again for this, then do the cross connection again. And then what you get essentially is you get a self-reconstruction at the end of your cat again, right? So you're taking appearance of the cat and the content that you're getting from here. At the end, what you have done is you have reconstructed the cat, right, by going 2 laps. So that's the basic structure of encoding your image representations into content and appearance, and having generators to generate images, right? So you can have different loss functions here. So the first loss function is like a cycle GAN cross reconstruction loss. Basically, try to minimize the loss between the input image and the reconstructed image for both species, for both X and Y. Then you can have an adversarial loss, the domain adversarial loss for these 2 generated images. So this particular loss function would essentially try to fool the network that, hey, is it a realistic image looking? Is it a realist image or is it a fake image, right? So the task of this particular loss is to fool the network and produce more realistic looking images. You're saying cat face, sorry, what?
I mean, like, the cat space is black and the dog space is white, right? But the generated images didn't learn this pattern. So I'm just asking, like, is there any way you can specify which attribute?
Yeah. So the answer is yes. So we can sample from this, well, not part of this paper, but in general, we can sample from the latent space, all these encoded representations, and we can have a series of what kind of attributes we want in our final output. Yeah, so you can control that appearance factor in general in other generative modeling papers. Yeah. Yeah, so I think we have 5 minutes. I'll just wrap this up. And yeah, so this particular loss function helps in deciding or fooling the network to make it more realistic. Then same goes with this particular loss, adversarial loss function, which makes the network be known that this is actually a real encoded representation. Then we already saw the reconstruction loss, and finally, we also have losses on the latent space. So we have losses on these encoders, and we kind of put some explicit priors and make them more Gaussian looking like. so that we can sample from them easily and make sure that the network produces a wide range of images than producing from just a small distribution. I think these losses, I think you can look at them offline. I think, yeah, we can finish this. So where is this concept of decomposing your input images into content and appearance applied in medical images? Pretty much everything that you can think of these days. So you can use them for image registration, segmentation, image synthesis, federated learning, image translation, data harmonization. So essentially, you can use that disentanglement approach and also use it for domain adaptation and generalization. Yeah, so I think I've covered the main concept. I'll just go through a couple of papers. I'll share the slides. You can look them up. Exactly the same idea that we discussed in that slide. So here the task is you want to segment abdominal regions in your images, but at training time, you're giving a lot of CT images and you don't have much information about MR images. So at training time, you're giving CT images with a lot of label data, but at test time, you want to test them on MR images. So can we use disentanglement representations to close this domain gap between these two modalities? So that can be answered using domain entanglement as well. You can do other stuff. Again, content and appearance for these images. Incorporate your architecture choices from all the architectures that we saw. Do a reconstruction and get predictions for your segmentation tasks. Right. You can also tie this up with doing unsupervised deformable registration. So whatever you saw in the registration lectures, take that to deep learning. If you saw Vox and Morph, take that architecture, incorporate disentanglement into that, and you can convert a multimodal image registration problem to a monomodal image registration problem using disentangled representations. I think that's it for today. I had to rush through slides, but I guess the main concept was there in the introduction slides for every topic. Yeah, thank you. Let me know if you have any questions. So,
one closing thought, like, you guys are feeling overwhelmed with all this information. Just imagine what it would take to actually go through the literature and extract that information. So like, this is like amazing amount of distillation of thousands of papers and like years, I think, worth of reading papers and a lot of information.
Slides, young candidate.
Yeah, we can.
Wednesday.
Yeah, Wednesday.
Have any more questions? You can always email me or call or something. Thank you.
Yeah.